Okay, so I'd like to start this session. This is the first of the series of general lecture in this URSI GASS in Sapporo. My name is Makoto Ando, chairing this session, and I hope the active discussion, which is expected just after the talk, and please join this talk. The first general lecture is the Photonics for Next Generation Radio Access Network. It will be presented by Professor Masataka Nakazawa, and I will introduce briefly his history. After receiving doctor degree from Tokyo Institute of Technology, Dr. Nakazawa joined NTT Laboratories, and after staying a small period at MIT in United States, and he got the professor position at Tohoku University. And now the director of the Research Institute of Electrical Communication. He has been a distinguished professor since 2008. And he is now a director at large of OSA and a board member of IEEE Photonics Society. He was the past president of IEICE Japan. He engaged in research on optic solitons, ultra-high-speed transmission, and ultra-short pulse lasers that led on from his invention of the compact L-beam doped fiber amplifier, EDFA, which realizes the long-distance optical communication networks now. His recent research has focused on various approaches to digital coherent transmission, mode-locked lasers, and mobile front-haul transmission in 5G and 6G, which will be focused on today's talk. He already published more than 500 journal papers, and he received many medals and awards, including medal with the Purple Ribbon, the Japan Academic Prize, IEEE Quantum Electronics Awards, the OSA Charles Howard Towns Award, and recently the Japan Prize. Dr. Nakazawa is a fellow of the OSA, IEICE, JSAE, AP, and a life fellow of the IEEE. So let's start the session. Please, Professor Nakazawa.
Thank you very much, Professor Ando, for your kind introduction. Morning, ladies and gentlemen. I am Nakazawa of Tohoku University. Well, first of all, I'd like to express my sincere thanks to the organizing committee for giving this opportunity to talk general lecture at URSI GASS conference in Sapporo. As Professor Ando mentioned, my title of the talk is Photonics for Next Generation Radio Access Network, RAN. And this is an outline of my talk. Well, first, I'd like to describe the recent progress in optical communication, where I'd like to focus on the challenges and efforts being made for a 1,000-fold capacity increase. That is, we call the 3-March technology. Then I will move on to the evolution of wireless systems from 5G to 6G, where I describe the digital radio over fiber as a optical mobile front haul. And the other one is analog radio over fiber, which is quite interesting as a wireless and photonics fully integrated coherent 6G system. Finally, I summarize my talk. Well, this figure shows a technological overview of optical fiber transmission, link capacity per fiber as a function of year. When we look back at the 1990, it was the age of first optical communication innovation with EDFA and its application of WDM. With this technique, capacity was increased from a gigabit per second to terabit per second. So we first thought that it is quite easy to handle the total capacity by just increasing the WDM number of channels. But when we increase the channel numbers, it means the total power, average power increases up to the a few watts. Then a very serious effect start to occur. That we call it the fiber fuse problem. You can see here the white light. This light propagates toward the transmitter with a speed of 1 or 2 meters per second. This fiber fuse occurs due to the very high power inside the core. That creates the plasma. And if once this fiber fuse occurs, optical light never can transmit through the fiber. So the 100 terabit per second transmission is a very high wall, but we couldn't overcome this 100 terabit per second limitation. On the other hand, when you look at the internet traffic, for example, in Japan, as a function of year, 1 terabit was achieved in 2009, and it will be 1 petabit per second at 2030. So the question arises as to whether the current technology is effectively accommodates the petabit per second capacity with any traffic congestion. And it seems to be difficult, so we proposed a 3M technology that means the multi-level coherent transmission, multi-core fiber, and multi-mode control with MIMO. So let's start from fast M, which is very popular for you. So far in optical communication, about 15 years ago, we used just on-off keying. So it's a 1-bit system, but in the field of wireless communication, you use the two-dimensional information coding. And in this case, we use the quadrature amplitude modulation, where we prepare the two axes in phase and the quadrature phase, and we can plot the information in 2 dimensions. So this was originally came from wireless, and now we use this technique into the optical communication because there's 2 reasons. One is a frequency of the laser diode. The fluctuation is very small, and the line width is less than 100 kilohertz. So we can apply the coherent technology into the optical communication. This one was reported from my group. It's a 4096 QAM optical transmission. You see, this is a 496 QAM constellation before the transmission. And after transmission, after 160 kilometer transmission, it becomes like this, and we see a fluctuation or the deviation for these edges, which is due to the somewhat from the nonlinear fiber optics. But when we employ the very strong further error correction technique with a 20% overhead, which is placed this dashed line, and this is a back-to-back, and after the transmission, the result becomes like this. So we can, with the use of this strong further correction technique, it seems to be possible to realize error-free optical transmission at 4096 COM. And I want to emphasize that the spectral efficiency becomes 15.8 bit per second per hertz. This is a very, very high spectral efficiency, because the total transmission bit rate is 72, and bandwidth is about 3.8 gigahertz, and this is 1.2 is error correction overhead part. So it's almost 16 bit per second per hertz. But so far, in the optical communication, since we just use the on-off keying, the spectral efficiency was less than 1 bit per second per hertz. So we can increase largely the efficiency of the optical transmission. Well, the second one is multi-core fiber for space division multiplexing, SDM transmission. I show here the 19-core multi-core fiber, 37 multi-core fiber, and this one is the 36 cores with 3 modes per core. So in total, 108 modes. To make these fibers, since we put a lot of cores, unfortunately the cladding diameter goes up to more than 200 micron, where the conventional fiber diameter is about 125 micron. So it is very important to reduce this cladding diameter. From a viewpoint of a commercial application, we will start to install the 4-core fiber or even 2-core fibers. And these fibers were fabricated at the Furukawa Electric Company, Fujikura Electric Company, and the Sumitomo Electric Company. All Japanese optical fiber company can make such beautiful multi-core fibers. Another interesting fiber is hollow core fiber. In ordinary fiber, as you know, the core part is, of course, the silica with a slightly high index than the cladding. But this one, the core is this center. The black part is air. So you may think that how we can confine the light beam in the air. But it is quite interesting to see the cladding part. We have two hollow core fibers. One is a photonic band gap fiber, and the other one is an anti-resonant fiber. In the photonic band gap fiber, we have this kind of a special two-dimensional photonic gratings. So if once the light beam in the core go outside, then that beam is reflected again into the core. The fiber loss is about 2 to 3 decibels per kilometer, still high loss than the ordinary fibers of 0.2 decibels per kilometer. On the other hand, anti-resonant fiber is quite interesting recently. Well, this one was reported from the Optical Research Center at Southampton University, and this part, center, is a core, and this thing, a capillary, double capillary, act as a cladding. Physics behind this structure is that you see this thing, a glass plate, act as a Fabry-Pellot resonator. And usually we use the passband of the Fabry-Pellot resonator as a monochromator, but in this case, reflection part is utilized. So this is a very clever idea to confine the light beam into the core part. And this one, surprisingly, realized a loss of 0.17 per kilometer, decibel per kilometer, which is almost the same as those of conventional fibers. So it's quite interesting. Additionally, this part is air, so the light beam can travel faster than the conventional fiber. That means information can carry faster than any other fibers, which is quite useful for economical, banking and stocks. Well, the third one is a multi-mode control with a MIMO. In order for you to increase the transmission capacity in the wireless communication, of course, you increase the number of antennas in the transmitter and the receiver. And we have a channel matrix here. And the wireless people developed the MIMO technology, which is quite interesting to classify the mixed signal into the each independent signal. The similar things happened when we use the multi-mode fiber. But so far, I described the single mode fiber, so only one mode transmit in the fiber. But in this case, a mode division multiplexed fiber using a MIMO. So we use the many higher order modes and prepare the many transmitters and receivers. So this is the formulation of a MIMO technique, and it is very important to note that the system is Aramid. Then we can orthogonize the this channel matrix. We can orthogonize this matrix. Then we can send the many information through these modes. This is a few mode fiber instead of single mode fiber. So in this case, the core diameter is slightly larger than the conventional single mode fiber. So we can carry not only this single mode mode pattern, but also the higher order modes. And we can send the different information with these modes. For example, we use the modes from LP01. This is a fundamental mode, and from two LP02 modes, so six modes is utilized. And we can also increase the capacity double by using a polarization. So in total, we have 12 modes, so we need 12 by 12 MIMO technique. The middle one is a coupled core fiber. So these fibers are mutually coherently coupled by changing the phase of each core. And the right-hand side, this is a multi-core few mode fibers. Recently, the 10 petabit per second transmission has been reported. This is a very preliminary experiment, but it is very important that optical communication now reaches the 10 petabit per second transmission age. So the upper one is 19 core, the 6 modes, and 739 WDM condition. With a 12 by 12 MIMO, and the fiber length is just 11.3 kilometers. So very short transmission, but it is interesting to see that 10 petabit can be seems to be possible. The lower one is, this one was reported from the KDDI people, and the lower one is from NICT in Japan. They used the 30 core by 3 modes and 368 WDM and 6 by 6 MIMOs. In this case, again, the 10 petabit transmission was achieved, although the fiber length is just 13 kilometers. Now, I'd like to move on to the evolution of wireless system from 5G to 6G. This view graph shows the progress on the mobile communication systems, and on the left show the mobile traffic capacity per year, and you see the download capacity is largely increasing. And on the right side, I show the wireless transmission peak rate. In 2020, it's about 1 gigabps, but in these days, it reaches 10 gigabit per second. And when we draw the line toward this direction, in 2030, it will be 100 gigabit per second. So even in wireless communication, we use 100 gigabit capacity. That means, the petabit transmission in the trunk transmission line must be developed. Okay. This is a roadmap toward beyond 5G or 6G by Ministry of Internal Affairs and Communications in Japan. And in the 5G, it's 10 gigabit per second, 1 millisecond latency, and 1 million connectivity, but it will be improved to 10 times, and the latency is 1/10, and again, the connectivity is 10 times. In addition to those requirements, we have system must be ultra low power consumption, and also the ultra security and resilience has to be realized. And I show here the evolution of a radio access network architecture from the 5G to 6G. So we have information from the core network, and at the central office, we convert the information into the wireless data using CU and DU. And that data are transmitted through the fiber. This part is called optical mobile front haul. We need optical fiber transmission because the wireless capacity is gradually increasing. And in this case, the cell radius is less than 100 meters, and the carrier frequency is like this. When we look at the 6G system, we have many remote units, because when we increase the carrier frequency, the wireless beam doesn't propagate long distance. So we need a lot of cells, and distributed antenna is needed. I summarize here the 5G specification, the 6G specification. 10G has to be 100. The 1 millisecond latency should be less than 0.1 millisecond, and the connectivity is 10 million devices per square kilometers. Now, as a optical mobile phone, we have many methods, which are classified into mainly two categories. One is digital LOF, where we have a non-coherent PON and a coherent PON, and the other one is analog LOF and the subcarrier non-coherent PON and single carrier fully coherent, where we have self-heterodyne type and heterodyne type. The first one is DLOF, and the configuration of DLOF is as follows. Well, it is needed to convert the wireless signal into the optical signal, since we use the optical transmission. Although it is very a short distance, but we need to convert the wireless information into the photonics information, where we use the SIPLI optical interface. It's a common public radio interface is needed, where the 16 times transmission capacity is required to convert the wireless data into the photonics. So if we want to send the 1 gigabit per second wireless information, we really need 16 gigabit per second transmission in this mobile front haul. So that is not so good. And in addition, the AD, DS, SIPLI framer and the deframer have to be installed for each antenna. So the difficulty to realize we have a difficulty in the low-cost system. So first, non-coherent PON, which is a very simple and low-cost system, but the capacity is about 40 gigabit per second at most. So this is a very simple 10 gigabit WDM on-off king PON system between a baseband unit and remote radio head. WDM technique with SIPLI is utilized. So very simple technique. Now this is commercially available. And now the coherent PON, I show the advantage is a high capacity, but we need a little bit complex system and expensive, a little bit expensive. This is a 10-channel 5 gigabaud, 256 QAM. In total, 800 gigabit per second bidirectional mobile front haul using a coherent WDM PON. This is a baseband unit. We prepare the 10-channel, and this is the downlink. The uplink is also the 10-channel. This is a photo of 800 gigabit digital coherent mobile front haul system that was constructed in my research group. And one of the channels is online transmission. So I show this is a downlink spectrum. This is uplink spectrum. And when we use coherent transmission, backward wireless scattering from the opposite side is mixed with the transmitted signal. So we have unwanted coherent interference, and we should remove such interference. So we shifted each carrier frequency by 10 gigahertz. And this is the result. When we assume the forward error correction level of 3.3 times 10 to the minus third, all signal became error-free condition. And when we employ the 14% overhead head decision FAC, error-free transmission was realized in the online condition over the 10 kilometers. The last one is analog over fiber, radio over fiber, as a wireless photonics fully integrated coherent 6G system. So this one has two ways, and we want to emphasize the fully coherent system in which you have two ways. One is the self-heterodyne type, and the other one is the heterodyne type. Self-heterodyne type is a simple configuration and a low-cost system, and local oscillator is not needed. But because we have to send the tone signal through the fiber, so the signal-to-noise ratio will be degraded. So system performance is not as much as those heterodyne type. But this one is quite interesting. And the system is like this. The difference is, let's see. This is a digital radio fiber. We use the ADDA series, but now we remove such devices. We directly send this wireless information through the fiber. So at the receiver side, we need self-heterodyne detection with a high-speed photo detector, where the characteristics is the IF signal can be simply generated without a local oscillator. Signal-to-noise ratio of the generated IF signal may be degraded, since the tone signal is, as I mentioned, also attenuated through the fiber transmission. Third one is bit errors in the photonics can be corrected by wireless FEC. FEC in photonics may be removed, which makes the system simple with a lower latency. I showed there two examples of this self-heterodyne type coherent mobile front haul. One is this one. This was reported by the people of NYCT. They prepared intermediate frequency at 92 gigahertz. We prepared two signals. One is data, the other one is a tone, and both are transmitted through the 10-kilometer fiber. And after their transmission, these two data are mixed with a high-speed photo detector, and this difference gives us the IF signal. So, although the transmission distance is just 1 meter, but it's quite interesting to realize the in this case, 11-bit gigabit per second capacity was transmitted. High IF frequency, high capacity, and coherent technology was utilized. And this was the second one, again, the self-heterodyne type. And in this case, by using optical frequency COM generator, tone signal was set at about the 400 gigahertz. So IF frequency is 400 gigahertz. It's nearly a terahertz region, and the transmitted data is more than 100 gigabit per second. Techniques are almost the same, although they don't put the 10-kilometer fibers, but they directly they send it to the UTC means a unit traveling carrier photodiode, which works very high at a very high speed. And they generated 400 gigahertz IF signal and transmitted 50 centimeters. Now, last one is a fully coherent system with a heterodyne. This one realized the high SNR and the large capacity, although we need a local oscillator. So instead of a self-heterodyne system, just using a photo detector, we prepare the local oscillator. In this case, we proposed to use the injection-locked local oscillator as a carrier frequency converter. So the characteristics is as follows. IF signal with a high SNR can be generated with the use of an injection-locked optical oscillator, the local oscillator. According to our experiments, a 6 dB loss budget increase can be obtained compared with the self-heterodyne method. And again, the bit errors in the photonics can be corrected by wireless for the error correction. So if you see in the photonics may be removed, which makes the system very simple, low cost, and low latency. So I'd like to briefly mention about how to realize the injection locking of the local oscillator. As you know, in a wireless field, we have injection locking in the microwave oscillators, but the same things happens in the laser diodes. So we prepare two laser diodes. One is a master laser, and the other one is a slave laser. So this master laser acts as a tone signal, and the slave laser acts as a local oscillator. So master laser signal is coupled into the slave laser, then the slave laser's frequency pulled toward the master laser. And when the injection lock occurs, the whole information at the master laser is copied into the slave laser. So after the injection locking, intermediate frequency becomes very narrow, like this. This acts as a IF signal. Well, I'd like to explain how the injection locking occurs in the Fabry-Perot laser diode. Well, without the injection locking, the spectral profile of the Fabry-Perot laser diode is very broad, as you can see here, like this. But if once we inject the narrowband signal into the Fabry-Perot lasers, the spectrum becomes like this. When we expand this spectrum, it becomes like this. And by integrating a whole a spectral component as a Fourier frequency, the single sideband phase noise was estimated to be 0.24 degrees. This is sufficient to send the 256 QAM signals. And it is also important how the injection locking actively maintains the phase information. So this view shows the performance difference of injection locking against the phase change. We artificially prepared a phase change by the pseudo-random pattern. And this is a bit signal. This blue one is how the artificial frequency fluctuation occurs. And when we adopt the Fabry-Perot laser diode, which respond very at a very high speed, so wide range frequency locking is possible, then all phase noise can be removed. On the other hand, when we use the, for example, external cavity laser diode, which has a very high Q in the cavity, and very high performance, but bandwidth is narrow. So as you can see here, red colors, the frequency near the zero frequency can be completely phase locked, and fluctuation is removed, but higher frequency part is not possible to completely remove the phase fluctuation. This is the 64 gigabit per second, 256 QAM heterodyne type fully coherent mobile front hole. The wireless signal is from AWG, and this is a data signal part. This is a tone part, and coupled into the signal fiber of 10 kilometers. At remote unit, the data signal is through, and tone signal is coupled into the laser diode. So this part is injection locking part. So very weak tone signal is eventually becomes very strong low phase noise tone signal. In a self-heterodyne system, we have to use this attenuated tone signals. But in this case, just installing the one laser diode can recover these attenuated tone signal into the high intensity low noise, a local oscillator signal. So when we take a bit signal between these two signals at for example, the pin photodiode, then we can generate a very low noise IF signals and QAM data. And after the 40 kilometer transmission, we use the phone antenna to measure the to investigate the data transmission performance by using a DSP. This is an experimental setup. This central office part and remote unit. This is a antenna, and this one is a DSP type, DSP part. Okay, this is the result. 8 gigabaud, 64 to 256 QAM bar performance after 10 kilometer fiber and 40 meter wireless transmission. We did 3 cases, 64 QAM, which is can generate 48 gigabit per second, and 128 QAM gives us the 56 gigabit per second. And when we adopt the 256 QAM, it reaches 64 gigabit per second. So when we plot the bar as a function of QAM multiplicity, when we use the forward error correction threshold with 25.5% overhead, even after the transmission of 40 kilometers through the air, it seems to be we can generate the error-free transmission. Well, this one is, with this figure, I'd like to emphasize that how we can integrate the photonics and wireless communication. So performance control of optical transmission part with wireless FEC. This one, the vertical axis wireless throughput as a function of a signal-to-noise ratio of the wireless signals. We did experiment in the optical region, and simulation was done in the wireless part. And this black line was obtained with wireless and optical forward error correction. 2 forward error correction techniques are simultaneously utilized. So when we increase the SNR, the throughput becomes gradually increased. When we do not adopt the optical forward error correction, and keeping the OSNR, optical SNR of 23 decibels, then a curve becomes like this. So there's a certain amount of deviation from 2 curves. But when you look at the SNR of less than the 70 dBs, both curves overlapped completely, which means there's no need to use the optical forward error correction. So we can treat the optical and the photonic system as a one system. And if we want to increase this throughput much more than this one, then we need to increase the OSNR of photonic part. By eliminating the optical forward error correction, which is about 14% overhead, the transmission capacity of the optical front haul can be increased, the 1.14 times. The system is simplified with ADDS, and a low latency can be achieved. This is the last view graph. In my talk, I emphasized the carrier frequency converter, in which the very wideband photonics photo detector is needed. In addition to the such a high-speed photo detectors, we need other optical devices and high-speed electronic devices. So as a frequency conversion devices, we need UTC-PD, which acts as more than the 100 gigahertz frequency, the PIN photodiode, indium phosphate, and gallium nitride HEMT transistors, and high-performance electrical amplifiers at 100 gigahertz will be strongly needed. In addition to these OE conversion, we need E to E conversion, and graphene mixers and ultra-fast double balance mixer will be needed. On the right side, I showed the silicon photonics. Well, the electro-optical integrated devices employing silicon photonics will be a key technology to realize this kind of fully coherent 6G mobile front haul. And in these days, silicon photonics is strongly evolving, and in the near future, this very tiny chip enables us very helpful for the 6G system. So in summary, recent challenges for optical communication and next generation radio access network, especially for optical mobile front hauls, has been presented based on the fact that a difference between the wireless and the photonic communication systems is only a carrier frequency. I emphasized the fully integrated coherent mobile front haul system, which can directly connect the wireless and photonics systems. This technique will become an important technique to realize a simple 6G system configuration with a low latency and a low cost. In addition, advancements on the high-speed photonic and electronic integrated devices will be key technologies for realizing a 6G system. So this concludes my talk. Thank you very much.
Thank you very much for the nice talk, Professor Nakazawa. So we have time for the question and comments. So please raise a hand and please use the microphone. Okay, please.
I'm Akira Hirose, University of Tokyo. Nakazawa Sensei, thank you very much for the very encouraging and insightful talk. I'm personally impressed by the extension of the coherent technology in optical communications.
Yes.
Proposed by Professor Takanori Okoshi almost 40 years ago, I think, and who also served as the general chair of the URSI GASS 30 years ago. And well, by considering the changes of the society in these 30 or 40 years, we are very much surprised by the fact that communication technology changed our lives in various aspects. We didn't imagine this situation using many mobile devices and Zoom and other online systems and so on. Well, the technology itself realized the faster, low latency, wireless aspects in the hardware and software and everything systems. But the result is also have been very influential to the society, human society. And my question is very general. I'd like to receive a little more insights from you, Nakazawa Sensei, about the changes of our society, human society, probably realized by the great technological development.
Well, it's a very difficult question to answer. The history of the communication, always we search the higher performance. I hope such a system will effectively work for the life of human life from a good aspect. But on the other hand, when we use this high-tech system into the for example, war, and it would be not good. So we should keep in mind that this technology should be used to improve the human life. I'm not sure this is the answer for you, but I don't know.
Okay.
Yeah. Sorry.
Question is general and the answer is also general. Okay. Thank you very much. So next question. Okay, please use the microphone.
Yes, thank you very much for a very nice presentation. So my question is about the multi-mode fibers. And when you use MIMO to send multiple streams in parallel down a multi-mode fiber, are the parallel streams, is it one stream per mode, or is each stream spread across the multiple modes?
It's a multiple modes. Let me show you.
So each mode contains a portion of all streams, is that correct?
Yes.
So then, does the multi-mode dispersion limit the distance of propagation that is practical?
Yes.
Okay, thank you.
Well, let me explain about that a little bit more. Let's see, something like this. Sorry. Well, we send different mode. So as you mentioned, the group velocity of each mode is different. So we want to use all modes, but as you mentioned, the speed is different. So it is difficult to make a channel matrix at once. So for example, most people use the 6x6 MIMO. That means these 3 groups, which travels almost at the same speed. When we incorporate these group 5 modes, they are very slow. So it is very difficult to make a large matrix. So partial MIMO is used.
Thank you very much.
Thank you. Is there any questions? Is there? If not, I have one question.
Yes.
You mentioned about that hollow core.
Oh. Yes,
you mentioned that the speed of the group,
Yes.
delay is much faster than the conventional one, and which is very attractive for the people in finance or fintech.
Yes.
Means they are worried about the slowness of the optical signal. Is it correct? You mean this fiber have a much faster group delay speed?
Yes, you're entirely right. When we use this fiber over long distances, then delay between a silica core fiber and air core fiber becomes quite large, a millisecond or a few hundred microseconds. Then when we send the data signal with very high speed, so megabit or gigabit information can be obtained than the silica core fibers. So as you mentioned, people who use the silica core fiber want to replace the fiber into the air core fibers. And some GAFA company are going to use this fiber, and people at the ORC, Optical Research Center at Southampton University, joined such activities. So internet people are very much interested in this hollow core fibers.
Okay, thank you. One more question is, most of your talk, especially for the self-heterodyne types of, network, in that case, you mentioned about you are assuming the link length very short. Experiment a few meter, and you mentioned about the 30 meter or 40 meter for the link length of the mobile front fold. What would be the typical length in 6Z in near future?
Well, the photonics part, I think 10 kilometers or 20 kilometers is a appropriate length, and as for the fiber, the loss is about 0.2 decibels per kilometer. So it is not so a big problem to send 10 kilometers or 20 kilometers. So when you think about the very high frequency wireless transmission, in this case, you see here the IF frequency is 92 gigahertz, and they use the UTC-PD, but unfortunately they could not prepare the appropriate electrical amplifiers. If they can install the electrical amplifier in front of the photodetector, then transmission distance will be much extended than just 1 meter. So the similar things happened in this case. Just this one is a 400 gigahertz carrier frequency, but transmission distance is only 50 centimeters.
50 centimeters.
So this should be improved largely, but again, they could not use the a 40 gigahertz amplifier, electrical amplifier. If they have, this 50 centimeter distance will be increased. So,
okay. Thank you very much. Is there any question? We have some more time. Okay, please.
Thank you very much for a very impressive talk. And I have the question related to the second question. And can you go to page 11?
11?
Yes. Yeah. I have also a question about the MIMO implementation. So I now understand that the number of modes are very limited, but I am still wondering, comparing between the number of cores and number of streams, the stream number is much smaller. So I just wonder, what is the limitation to reduce the number of the channels finally in the MIMO transmission? Is it due to the digital circuit or due to some power imbalance? Or I am just curious about what is the limiting factor that you are not able to increase the number of MIMO channels.
So you're talking about the number of the WDM channels?
Yes, yes.
I think the total power will be almost 1 watt or 2 watts. So they want to further increase, and it seems possible because of a very short distance. But when we assume the 100 kilometer petabit transmission, it would not be possible. So I think 700 WDM channels is at the most in terms of the power limitation.
Yeah, thank you very much.
Okay, is there any other question? Okay, if not, I would like to thank Professor Nakazawa for the exciting talk and for the question. Once again, please give him the appreciation. Thank you very much. Thank you very much for attending this general lecture. Please enjoy the other series of general lecture in this conference. Thank you very much.